we will explore the stainless steel production process and the automatic motor production line. In the following videos, we will learn about the repair and maintenance of steam turbines and large generators. Stainless steel production is a fascinating process that results in shiny, new-looking products, even when they are made from scrap metal. The transformation of stainless steel involves recycling old sinks and pots to restore their former luster. The entire process begins by loading the materials into a furnace where nickel and chromium are added to enhance strength and corrosion resistance. The mixture is heated using giant electrodes until it reaches its boiling point, creating a spectacular fireworks-like display. After several hours of boiling, the mixture is poured into a refining furnace. Argon and oxygen are introduced to the furnace for purification. Impurities are converted into gas, while others remain on the surface and are drained as waste. A metallurgist closely monitors the temperature and takes samples to control the chemical reaction in the furnace. Adding scrap metal during the boiling process increases the volume of the mixture and accelerates the chemical reaction during purification. Next, the bubbling steel soup is poured out of the furnace and passed through rollers to form a long strip measuring 70 meters in length. A special torch cuts the flat rolled blanks, and each blank is marked by a steelworker using a hot pencil on the glowing metal. The blanks are then transferred to another section for further processing. The blanks undergo another heating process to soften the metal. The resulting rust film is removed by high-pressure water jets without cooling the hot metal. The softened blank is then rolled using mill rolls that are constantly cooled with water, simultaneously stretching and elongating the steel. At this stage, the steel strip reaches a length of approximately 600 meters. The stretched blank is slightly cooled with water to make it soft and flexible for coiling. A coil winds the steel sheet like toilet paper. The coiled steel roll is transported to another section where it is washed with hot acid to remove rust deposits. In this unit, the steel is also heated and then slowly cooled to reduce mechanical stress in the metal and make it more malleable for further processing. The steel is then unwound and rolled to the desired thickness. During the rolling process, the cold steel hardens, closing the pores on the surface and giving it a shiny appearance. The final treatment gives the stainless steel its dazzling finish. When exposed to atmospheric oxygen, the chromium in the steel forms an oxide film that protects it from rust. Finally, rotating knives trim the edges and cut the sheets to the required dimensions according to customer specifications. It truly is a brilliant process that produces high-quality stainless steel products. The maintenance, repair, engineering, and overhaul (MRE&O) process for steam turbines is a meticulous and comprehensive undertaking, and Ethos Energy is a recognized expert in this field. Their expertise ensures that steam turbines operate at peak performance, minimizing downtime and maximizing efficiency. In rotor machining step, technicians can restore damaged or worn-out rotor components to their original specifications, ensuring optimal performance and longevity of the turbine. They execute the machining process, paying close attention to dimensional accuracy and surface finish. Technicians perform thorough dimensional analyses to evaluate the structural integrity and dimensional accuracy of turbine casings. Boring operations are conducted when necessary to restore proper clearances and ensure the correct fitment of components. This attention to detail guarantees optimal turbine performance and longevity. Operational speed balancing is critical for turbine efficiency, and they has the expertise to optimize turbine operation within specified speed ranges. They maintain a stock of spare bearings and oil seals, enabling prompt balance corrections and minimizing downtime. The facility's expertise extends to blade manufacturing. Their advanced capabilities, such as 5-axis blade milling and reverse engineering, allow them to produce high-quality turbine blades with precise shapes and profiles. This ensures optimal aerodynamic performance and turbine efficiency. When critical repairs are needed, Ethos Energy employs sub-arc welding techniques. Skilled welders utilize this process to maintain the structural integrity of turbine components. Post-weld heat treatment is performed to relieve residual stresses and enhance the mechanical properties of the welded joints, ensuring long-lasting repairs. Throughout the MRE&O process, the facility's engineering expertise is invaluable. Their team of experts provides comprehensive support and solutions, leveraging their deep understanding of steam turbine systems. Rigorous quality control measures, including metallurgical analysis and non-destructive testing, NDT inspections, ensure the integrity of repaired components. The generator repair process at Ethos Energy Generator Services in Farmington, New Mexico, is a comprehensive and meticulous endeavor that ensures the restoration and optimal performance of generators. The repair process begins with faro arm measurement, a cutting-edge technology used to obtain precise measurements of generator components. This step ensures that the repairs are carried out with utmost accuracy. Component engineering plays a vital role in the repair process. Expert engineers thoroughly assess the condition of the generator components and devise effective repair strategies. Their expertise ensures that all issues are addressed efficiently. Rotor winding is a critical step in the repair process. Skilled technicians meticulously wind the rotor to precise specifications using advanced techniques and high-quality materials. This ensures that the repaired rotor operates optimally, enhancing its performance and reliability. High-speed balance is another crucial aspect of the repair process. With advanced equipment capable of high-speed balancing, up to 4,150 RPMs, Ethos Energy ensures that any potential vibrations or disturbances are eliminated. This step minimizes wear and tear on the rotor and extends the overall lifespan of the generator. Stator electrical testing is performed to evaluate the electrical integrity of the stator windings. By subjecting the stator to rigorous testing procedures, any potential faults or issues can be identified. This allows for precise repairs, ensuring the stator functions optimally. In cases where stator bar replacement is necessary, Ethos Energy offers stator bar manufacturing services. With their facility in Poland, they produce high-quality stator bars that meet industry standards. These durable replacements are carefully installed by skilled technicians, ensuring proper alignment and connection. Machining of parts is a crucial step to ensure the proper fit and function of various generator components. Ethos Energy's in-house machine shop, equipped with CNC capabilities, allows for the precise manufacturing of parts tailored to the generator's specific requirements. The Nide Group's automatic die casting line is designed for the efficient and automated production of rotor die casting for multiple motors. The line is capable of fully automating the rotor production process. The basic specification of the line includes an 850-ton horizontal die casting automation system with options for 1 or 2 outputs. The line features automatic casting of aluminum into the shaft and manual weighing of laminations. It can also be integrated with an automatic slicer to achieve complete automation of the entire production line. The production process starts with manual weighing of loose laminations. The truss is then placed into the turntable, and a robot handles the loading process. The truss is moved into the tooling where die casting takes place. Once the rotor is casted, it is removed from the tooling and placed into the integrated machine. At this stage, the rotor undergoes weighing, marking with codes, inspection, and stamping. The rotor is then moved to the pressing machine, where the false shaft is pulled out, and oil spraying takes place. The real shaft is then picked and loaded, and the pressing process is carried out. Finally, the pressure head is removed, and the finished rotor is unloaded into a designated box. The technical proposal for the line includes various components such as waste frame, heat preservation furnace, soup feeder, 850-ton die casting machine, integrated testing and marking machine, axle press, finished frame ejector, robot, shaft setter, material storage disc, feeding truss, film processing table, and a dummy shaft return line. The automatic stator production line is designed to streamline the manufacturing process of single-phase motors, specifically for applications such as water pumps, washing machines, and fan motors. The production line incorporates highly automated features for stator loading, testing, insulation paper inserting, winding and inserting, middle forming, lacing, and final forming. The production process begins with stator loading, where the stators are placed onto the production line for further processing. Subsequently, stator testing takes place to ensure the quality and functionality of the stators. Following the testing phase, insulation paper is inserted into the stators to provide electrical insulation. The next step involves winding and inserting the wire into the stator slots. The wire size used ranges from Phi 0.18 mm to Phi 1.2 mm, and the filling rate of the wire in the slots is determined by the specific wire and slot sizes. Once the wire is in place, middle forming techniques are employed to shape and secure the stator windings. After middle forming, the lacing process is performed to further secure the stator windings. Lacing involves tying and fastening the wires in a precise manner to ensure structural integrity. Finally, the stators undergo final forming, where they are shaped and finished according to the required specifications. The entire production line is designed to accommodate stators with outer diameters OD of up to Phi 150 mm and inner diameters ID of up to Phi 110 mm. The stack length of the stators can range from 30 mm to 120 mm. The dimensions of the production line itself measure 15,000 mm in length and 6,500 mm in width. The production line is equipped with advanced machinery and automation technologies to minimize reliance on manual labor, thereby reducing production costs and increasing efficiency. The line features automatic functions such as stack adjustment, phase paper loading, stator loading, testing, data display for the entire line, and remote control capabilities. Nide Group, a renowned manufacturer in the field of electric motors, has introduced an advanced and efficient three-phase motor stator manufacturing production line specifically designed for washing machines. This innovative production line utilizes cutting-edge technology and automation to streamline the manufacturing process, increase productivity, and reduce labor requirements. The production line consists of several machines, each serving a specific function in the stator manufacturing process. The first machine in the line is the stator paper inserting machine. This machine automates the insertion of insulating paper into the stator slots, ensuring precise and accurate placement. The automation of this process eliminates the need for manual labor, reducing the chances of errors and enhancing overall efficiency. The next machine in the production line is the stator coil winding and coil inserting machine. This machine performs the crucial task of winding copper wire around the stator core to create the stator coils. It also inserts the coils into the stator slots with precision. The automation of this process ensures consistent and reliable coil winding, contributing to the overall quality of the motor stator. The motor stator production line developed by Nide Group incorporates state-of-the-art features to ensure seamless operation. One of the key highlights of this production line is the integration of app remote operation, allowing operators to control and monitor the entire manufacturing process from a central location. This remote operation capability enhances convenience and flexibility, enabling efficient management of the production line. After the coils have been inserted, the stator coil lacing machine takes over. This machine secures the coils in place by lacing them with specially designed wires. The lacing process not only enhances the mechanical stability of the stator, but also provides electrical insulation between the coils. By automating the lacing process, this machine ensures uniform and reliable lacing, improving the durability and performance of the motor stator. The final machine in the production line is the stator coil forming machine. This machine shapes the stator coils into the desired form, ensuring they are properly aligned and compacted. This step is essential for optimizing the motor's electromagnetic properties and reducing vibration during operation. By automating the coil forming process, this machine achieves consistent and precise shaping, enhancing the overall efficiency and performance of the motor. One notable advantage of this stator production line is its reduced labor requirements. Compared to traditional manufacturing methods, this automated production line significantly reduces the number of operators needed to oversee the manufacturing process. The assembly of the Trent XWB, Rolls-Royce's highly efficient aero engine, is a meticulous process that involves expert craftsmanship and cutting-edge technology. Located at the Trent XWB assembly line in Dahlewitz, Germany, this facility is where more than 20,000 components come together to create this remarkable piece of engineering. The assembly process begins with the arrival of various engine components from different manufacturing sites around the world. These components include the fan blades, combustion chambers, turbine blades, and casings, among others. Each component undergoes thorough quality checks to ensure that they meet the stringent standards set by Rolls-Royce. Once the components are deemed fit for assembly, the process begins with the core of the engine. This includes the high-pressure compressor, combustion system, high-pressure turbine, and low-pressure turbine. Skilled technicians work meticulously to carefully fit each component together, following precise assembly instructions provided by Rolls-Royce. The assembly line is equipped with advanced robotic systems that assist in the assembly process. These robots aid in handling and positioning heavy components, ensuring accuracy and efficiency. They are programmed to perform repetitive tasks with precision, freeing up human technicians to focus on more intricate aspects of the assembly. One of the critical stages of the assembly process is the integration of the fan system. The Trent XWB utilizes a large-scale composite fan, which is made of lightweight and durable materials. The fan is carefully mounted onto the engine, ensuring proper alignment and balance to maximize efficiency and reduce vibrations. As the assembly progresses, the engine undergoes a series of rigorous tests and inspections. These tests include performance checks, vibration analysis, and thermal imaging, among others. Any deviations or anomalies are meticulously addressed before proceeding with the final stages of assembly. Once the engine is fully assembled and has successfully passed all quality checks, it undergoes a comprehensive ground test. This test involves running the engine under various conditions to simulate real-world operating environments. It allows engineers to evaluate its performance, fuel efficiency, and overall reliability. Finally, after a successful ground test, the Trent XWB is ready for installation on the aircraft. It is shipped to the respective aircraft manufacturer, where it is mounted onto the wing and integrated into the aircraft's systems. The rewinding process of the 6.1 MVA stator and rotor of the hydro turbine generator by Coral Engineering was a complex and meticulous undertaking. The project involved not only rewinding the stator, but also increasing the power output of the generator by 12%. Additionally, a new set of bars had to be designed, manufactured, and supplied, while the rotor also required rewinding. The process began in August when smoke was detected from Unit 2 of the generator. It was discovered that the stator had been burnt and the core was damaged, necessitating immediate repairs to mitigate revenue losses. A technical team was assembled to analyze the root cause of the failure and develop a comprehensive solution for the rewind. State bar is a specially designed type of bar used in the stator winding of electrical generators. It is characterized by its advanced insulation system and superior electrical conductivity, making it highly efficient and reliable. The bar is manufactured using state-of-the-art materials and techniques, ensuring optimal performance and longevity. One of the key advantages of state bar is its enhanced insulation system. It incorporates advanced insulation materials that offer exceptional thermal and electrical insulation properties. This insulation system minimizes the risk of insulation breakdown, preventing potential electrical faults and ensuring the safe and reliable operation of the generator. In addition to rewinding the stator, the project requested an offer for the rotor job as well. The rotor was identified as the root cause of the failure, with issues such as interval jumper problems, fan imbalance, and loose-fitting water pins. The facility supplied new pins and modified the rotor to address these issues. To meet the defined timeline, a considerable workforce was employed. At any given time, there were 50 people working on-site and an additional 65 people working on the production line in the coil factory. The production and delivery of the bars were carefully planned, with shipments sent in multiple parts. The initial batch consisted of the bottom bars, which were promptly installed, while the top bars were being manufactured.